Hello, I'm Pratibha Chaudhary from Indian Institute of Technology, Madras, and I'll be giving this talk on parameterized complexity of feedback vertex set on hypergraphs. So this is a joint work with Lachlan Ganesh from Institute of Mathematical Sciences, Chennai, Daniel Lokshanov from University of California, Santa Barbara, Fahad Panolan from Indian Institute of Technology, Hyderabad, and Saket Saurabh, who has a joint affiliation to both Institute of Mathematical Sciences, Chennai, and University of Bergen. So these are the contents of the talk. I'll start with an introduction, go over the literature review, briefly talk about our results, then talk about the approach for one of our results, followed by the algorithm, and later the conclusion. So we start with the introduction. So the problem is feedback vertex set on hypergraphs. The formal problem definition goes like this. We have an input, which is a hypergraph, a parameter k, and the question whether there exists a set of k vertices whose removal makes the hypergraph edge acyclic. So just to ensure that everybody is on the same page, we briefly go through what is a hypergraph. It is simply a pair of two sets. First is a set of elements or nodes or vertices, and the second is a set of non-empty subsets of X, also known as the set of hyper edges. And hypergraphs are basically generalizations of graphs with the relaxation or the feature that an hyper edge can contain any number of vertices. So consider the diagram here. We just have some nodes or vertices, and we have these shaded areas which form the hyper edges. We talk about parameterized complexity now. So many problems that are naturally found to be occurring in the real world are NP-hard. That is, we do not expect them to have polynomial time solutions. So for such problems, we have multiple approaches to tackle them, one of which is parameterized complexity, where we aim to restrict the combinatorial explosion to some parameter which is hopefully much smaller than the input size. And we try to look for something that we call as fixed parameter tractable algorithm. That is an algorithm with the running time of the type f of k and polynomial in n. So if we have an algorithm of such a running time, we see that it is an FPT algorithm. And note that whenever we talk about a parameterized result, it's usually always with respect to a specific parameter. And not all problems are found to admit FPT algorithms, and we refer to them as W-hard problems. And owing to some complexity theoretic assumptions, we do not expect W-hard problems to admit FPT algorithms. Moving forward, so feedback vertex sets are basically set of vertices. If you talk about graphs, it's a set of vertices whose removal makes the graph acyclic or makes it a forest. And there has been a lot of work done on feedback vertex set in graph theory. In fact, lots and lots. This table gives a brief overview of the results. So the first FPT results were of the running time of the type order k to the power k. We are talking about deterministic algorithms, and this was later improved. The base was improved to finally some constant, the first one being 37.7, which was very recently improved to 3.46. And talking about randomized algorithm, the first one was given in 2000, which was of the running time order 4 to the power k. And the most recent result, which was in this year itself, which was order 2.7 to the power k. So apart from these, we have also had a lot of work on some variants of feedback vertex set, or as we can say FVS, which include connected FVS, independent FVS, simultaneous FVS, subset FVS, and so on. So a brief summary of our results. So we start with recalling the problem definition, which was we are given a hypergraph and a parameter k, and the question is whether there exists a set of k vertices whose removal makes the hypergraph acyclic. Now, the removal of vertices can have different connotations. What happens to an hyper edge once a contained vertex is removed? Okay, so we have two possible ways to perceive deletion of vertices. The first one being weak deletion, which is you just remove the vertex or delete the vertex in consideration and do not disturb the hyper edge. Okay, so suppose I delete this vertex here, then basically I'll be just reducing the size of these two hyper edges by one. And the other one is strong deletion, which is actually more analogous to the deletion that we have in graph theory, which says that, okay, remove the vertex and also delete all its incident hyper edges. So if I do strong deletion of this vertex, I'll also be just removing this edge here and also this edge here. Okay, so now I talk about the incidence graph perspective. So for a hypergraph edge, its incidence graph is basically just a partition of its vertex set and edge set. And the edges in this bipartite graph indicate the containments of the vertices in the corresponding hyper edges in the hypergraph edge. So the diagram will help it make more clear. You can see that we have all the vertices on one side and all the edges on other side. And if a vertex was contained in a hyper edge, in the hypergraph edge, we introduce an edge between them. Now there's something interesting that happens here, which is that if there is a cycle found in the hypergraph, we actually find a cycle in the incidence graph as well. So basically a cycle in H translates to a cycle in G. Now, again, since now we have the incidence graph with us, what do the two variants of deletion translate to? Weak deletion basically reduces to the problem of finding a weighted FVS once we have this incidence graph, hence not so challenging problem. But if we talk about strong deletion, the problem reduces to finding a set of vertices in one partition of a bipartite graph such that if we delete these set of vertices along with their neighbors in the other partition, then the remaining graph is acyclic. So in this paper, we work on this variant of vertex deletion in feedback vertex set for hypergraphs. So the problem, as I explained, reduces to finding what we call as a dominating FES on a bipartite graph. And as you can see here, we say that once you delete the close neighborhood of a subset S from one of the partitions, then the graph should be acyclic. And not so surprising, this problem was found to be W2 hard. It's not very surprising because hitting sets, which is a generalization of vertex cover, is also known to be W2 hard when we look in hypergraphs. And here this result was found due to reduction from set cover. So since the problem is W2 hard, we look at some restricted variants of hypergraphs. First one being linear hypergraphs, wherein any two hyper edges in a graph do not share more than one vertex, and D hypergraphs where all the hyper edges are of a bounded size D. So what do these variants translate to when we look at the incidence graph? In a linear hypergraph, the incidence graph will be free of C4 cycles because any two edge vertices here cannot have more than two common neighbors. And for D hypergraphs, the incidence graph will just have this property that the vertices in the partition B will have the maximum degree of D. So our results are like this. General HFVS is W2 hard, whereas hypergraphs of for linear hypergraphs finding a feedback vertex set admits a randomized algorithm, an FPT randomized algorithm with such a running time. And for D hypergraphs, we again have a FPT algorithm, this time a deterministic one of the running time as this one. Moving forward to the approach. So I'll just talk about the approach for, I'll just talk about the approach for linear hypergraphs and the randomized algorithms that we found. So this is the approach. Recall that Becker et al. In the year 2000 gave the first randomized algorithm, which basically goes like this. You take the input graph and you find the reduce graph, which has no degree 1 vertices and no degree 2 vertices as well. We get rid of degree 1 vertices and we short circuit degree 2 vertices. So for a graph with minimum degree 3, there is a property which is that at least half of the edges are incident to the vertices of S, where S is any feedback vertex set. So this property is very useful because owing to this, we immediately get a randomized algorithm, which is you pick an edge at random, pick one of its endpoint at random, and then you just delete it. After this, you pre-process, that is, you make sure that the graph is again of minimum degree 3, and once again, you will have this property holding and you can repeat the process. So this particular algorithm by Becker et al. Gave, this was a randomized algorithm with a running time order 4 to the power k. So this is the same idea that we use in our paper, but with a lot of other variations. So recall that the problem was finding a dominating feedback vertex set on bipartite graphs. Okay, so what are we actually looking for is we want to find a set of vertices in the partition A such that when we remove these vertices along with its neighbors in the other partition, then the remaining graph will be acyclic. So notice that the deletion of the neighbors is quite crucial, and if you observe, actually if we just remove these neighbors, then also the graph becomes acyclic because we've picked the complete neighborhood of the solution set that we were seeking. So what do we do is that we focus on finding these vertices in B, which were neighbors of, which could be neighbors of some solution, actual solution from A. So we refer to these vertices as B's since they are just from the partition B, and to make it easier for you to remember that from which partition are we trying to pick vertices. So we're trying to pick some useful B's. What are B's? They're just vertices in the partition B whose removal will make the graph acyclic. And technically speaking, they are the neighbors of some actual solution. The actual solution was something that we were wanting to pick from A, whose close neighborhood deletion makes the graph acyclic. And are the B's useful B's bounded? No, we don't know this because they just form the neighborhood of some k vertices from A, and this neighborhood can be large. So what we can do is that we find some sort of pre-processing technique such that at least 1 over poly k of the edges are incident on this closed neighborhood of S, where S is a dominating feedback vertex set, that is the solution that we are seeking. So if we find such a pre-processing technique that ensures this property, then what we can do is that we can pick an edge at random, pick its endpoint in B, and with 1 over poly k probability, we will get a useful B. Okay. So this is what we refer to as the alpha covering property. So what we do is this: you pick a B at random, we pick some vertex from the vertex set B at random. Actually, we pick k square plus 1 B's at random. Why so? Because if we do so, then we know that we can say that by pigeonhole principle, there will always exist a vertex V such that V is adjacent to k plus 1 of these B's, the B's among the k square plus 1 that we picked. And if V is adjacent to k plus 1 B's, then these k plus 1 B's cannot have any other vertex that they share in the partition because it's a linear hypergraph. And hence, V must necessarily belong to every k-sized solution. Okay. Now, recall that we were talking about this property where 1 over poly k of edges are incident on the closed neighborhood of S, where S is a TFVS. So, as before, this gives us this algorithm where we pick an edge at random, pick the endpoint in B, and we mark and delete it. I'll explain what is this marking for. Okay, and then rest of the process is same as I explained for Becker-et algorithm, that you pre-process this again, pre-process the graph again, ensure the alpha covering property holds, and then you're back to the condition that holds for the edges. Now, can we simply delete a vertex? Okay, the solution set that we are looking for, we delete its close neighborhood. Okay, but when we delete the neighbors of a vertex in a solution, then we are removing this information or this possibility that there could be also some other vertex in the solution which also had some neighbors amongst the one that we just deleted because of their neighborhood to some other vertex. So basically the problem is that we cannot just delete a vertex because it will modify our input graph, and then in the modified graph we cannot claim whether the alpha covering property holds. So what do we do is that we save the neighborhood of the marked vertex. Okay, so when you pick this B, then you save the neighborhood, its neighborhood in A, and you create a set and add it to this sum family F. Okay, we maintain all these sets and we form a hypergraph out of it with this incidence graph GF. And what do we need to ensure is that G, which was our bipartite graph, union this new graph that we just created, there should also be C4 free, because we're going to combine the two graphs and then try to look for a solution. Okay, what is a solution? We want to find a solution that makes G acyclic and hit all the sets in F. Okay, we need to hit all the sets in F because F actually contains those sets where we necessarily have to pick something in order to ensure that the B's that we picked are deleted. So the problem reduces to something else now, which is hitting dominating bipartite FES. Okay, which is basically that you have a C4 free bipartite graph. Okay, with this partition, and additionally a family of subsets over A. Okay, such that the C4 free property that I just mentioned holds. And now we are looking for a set of size K from the set A such that the deletion of closed neighborhood of S is a forest, and also S is a hitting set for this family that we mentioned. Okay, so recall that I mentioned this alpha covering property. So how do we go about this is that we categorize the vertices in A, okay, based on their incidence to the vertices in B, and based on how they belong to the family, the sets in the family F that we were creating to retain the neighborhood of the B's that we were marking. So we categorize the vertices in A, we apply some reduction rules which cannot be talked about in detail here, and then ultimately what we get is that after deletion of all degree 1 vertices, the length of any degree 2 path, a degree 2 path is a path which is containing only degree 2 vertices in the graph, the length of any such path is bounded by um, this value which is polynomial in F, polynomial in size of the family that we were retaining. Further, for any solution, at least this many this much of all the edges are incident on the close neighborhood of the solution. Okay, so if you notice, we are kind of drawing an analogy to what we had in the Beckett-Tolles algorithm. So the algorithm is now like this: you pick a b at random. Basically, you pick k square plus 1 b's at random, and what we do is that uh, we say that, okay, there will always exist a vertex v such that v is adjacent to k plus 1 b's, and these k plus 1 b's do not share anything else in the other partition, hence we must belong to every case as solution. And now what we do is we retain the neighborhood of v and create a set out of it, add it to the family f. We pre-process the graph. Again, I mentioned that we'll do some categorization of the vertices in A, and then we will apply some reduction rules, which will ensure that the alpha covering property holds once again. And then we go back to this assumption that, okay, if we pick k square plus 1 b's at random, then we find some useful vertex. And we keep on doing this. This pre-processing is actually what will also keep reducing the size of this family F. And ultimately, when we reach a point where the size of the family is bounded by k square, then we prove that the the reduced instance becomes fpt times solvable. And hence the result comes to this, that for linear hypergraphs, we are able to derive an randomized FPT algorithm with the running time 2 to the power order k cube log k and polynomial in n. And the nature of this algorithm is such that for a yes instance of the input, the output is yes with probability at least 1 minus 1 over polynomial in n. And if the input is a no instance, then the output is no with probability 1. Okay, so now we conclude the talk. We showed that general HFES is doubly too hard. The linear hypergraph variant and D hypergraph variants admit FPT algorithms, one randomized and one deterministic. What else can be done is we can explore de-randomizing of the randomized algorithm. We can look for faster algorithms for linear hypergraphs, and the much interesting open problem of whether or not the problem admits a polynomial kernel. Again, I'm talking of linear hypergraphs. And also we can look at a more generalized perspective of extending the study of these variants, other variants of FES to hypergraphs. Thank you, and that's it.